Today we look at another application of antiderivatives where we use this to help us find area underneath of a function. Now the difference here today is that we won't just be working with one function, we'll be working with two functions. Okay? And our job or our task will be to find the area between two different equations. And so I want to put an example up here on the board. Okay? Let's say that we want to find the area between these two equations, y equals 4 and y equals x squared. Right? That'll be our task for this first example. Now, graphically what this looks like, okay, if I graph y equals x squared, that's just a parabola going through the origin. And if I graph y equals 4, that's a horizontal line which goes through the y-coordinate of 4. So the question is, we want to find the area between these two curves. So we kind of get a region that gets sectioned off, and we want to find this particular area separating those two curves. Okay? Now, using the methods that we talked about last time, we are able to solve this if we just make one small adjustment from what we did last time. Okay? If I was just to find this area right here, okay, and I'll go ahead and well, let me ask you, where are these points at right here? What are the x-coordinates of those points? If I'm coming along this parabola, when do I get to a height of 4? When x is equal to what? When x is equal to 2 on this side, and when x is equal to negative 2 on this side, right? Okay, because 2 squared is 4 and negative 2 squared is 4. Okay, so this over here, this is the ordered pair 2, 4. This is negative 2, 4. All right? So if I was asking you to find this area from negative 2 to 2 of 4 dx, what I would be asking for, I'll draw another picture off to the side here. Okay, I would be telling you, draw the line y equals 4. I'll just draw a straight line here. Here's y equals 4. And I would be asking you to find the area underneath the curve from negative 2 to 2. So I would be asking you basically, find the area of this rectangle from negative 2 to 2 underneath of a height of 4. Okay? And that would be very simple to do. We wouldn't even have to do any antiderivatives. We could just use some geometry to figure that answer out. Okay? If I was asking you, find the area of x squared from negative 2 to 2, what would I be asking for? Well, again, let me draw another picture here. Okay? Here's x squared. If I ask you to find the area from negative 2 to 2, we draw these lines up wherever negative 2 and 2 are at. This probably should be a little more symmetric. Okay, so maybe like right here. Okay? And the area that you would be finding would be this area down here. The area underneath of the curve from negative 2 to 2. Okay, now, the reason I took all this time to draw out these pictures is I want us to make a comparison between this area right here, this area down here, and then this area in here. Okay? If I know this answer, and if I know this answer, how can I get this answer over here? I just have to subtract them, don't I? I mean, you can just see geometrically, this is the entire rectangle. So if I come in here and I draw some rectangles in here, okay, from negative 2 to 2, okay, that would be the area of the whole rectangle. That's 16. You know, 4 by 4 would be 16. Well, that's a little bit too big. But if I subtract off these extra pieces over here, which is exactly this region, then I have the area that I'm looking for, this little parabola-shaped type region here. Okay? And so that's what we mean when we talk about finding area between curves, is we take the upper function minus the lower function, and we find those areas between those values where those functions intersect each other. Now, the nice thing is we could solve the problem this way, but we really don't have to treat it as two separate problems. If we have the same boundaries, there's a rule with calculus that says you can join this together as just one single antiderivative problem. Okay? All we've got to do is just subtract the functions. So 4 minus x squared dx. So the first line is equivalent to the second line. And usually when we're writing these problems down, we usually never write the first line. We just realized that, yeah, I can synthesize that into just one antiderivative. We write it as a subtraction on the second line and we're finished. Okay? Now, if I want to find this area, well, this is a problem like we did last time. Hey, let me bring it up to here. All right, what's the antiderivative of 4? 4x. What's the antiderivative of x squared? X cubed divided by 3. Okay? Now I want to sub in some values for x. I want to sub in -2 and +2. Okay? So x equals -2, x equals +2. Okay? And I want to find this value. Now, before we do this, before we plug in the numbers, I just want to show there are other approaches as well. Okay? If we can ever get 0 involved as an x-coordinate, that's usually nice because usually we just come up with nothing. Okay? How would this area here, from -2 to 2, how would that area relate to the area from 0 to 2? You know, if I just found this area on the right side, how would that be related to this total area in here? It's half as much, isn't it? Okay? So another option, and you don't have to do this, but another option is, if I want to take away this -2, if I want to put a 0 in there, and if I want to find the area from 0 to 2, I could do all that and then just take my problem times 2. Wouldn't that give me the same answer? Okay? So there are some other little tricks that can be used here because we're doing just area work. Okay? And again, the reason I like to look for those kind of tricks is because if I can get zeros in here, it makes my calculations easier. Okay? All right, so now if I sub in 2 into this function, I'm going to get 8 minus 8/3. And whatever that number is, I need to multiply it by 2 because I want that area to be multiplied to capture the other side. Oh, I don't know what this is here. 5 1/3, I think, times 2. So if I did that correctly, which is not a guarantee, this will be 10 2/3 as your total answer. Okay? All right? Like I said, if you don't recognize this, if you sub in 2 and find the answer, and then you plug in -2 and find the answer and subtract them like we did last time, you'll still get the same answer. Okay? Just to me, it's a lot easier if we can ever get 0. If 0 is ever symmetry within a graph, I go ahead and try to use it. Okay? So there's one example of area between two different curves here. Okay? All right. Picking on another example here. What if I tell you find the area between these two curves? Y equals x squared minus 30 and y equals 10 minus 3x. Okay. Now, the first thing that's usually a good practice is we want to graph these functions, and we can either graph them by hand or we can come to the calculator here. Because one of the things that we will need is we'll need to know what this graph looks like. We need to know what region we're trying to solve for here. 10 minus 3x. Okay. Now, if I graph this on a standard window, I may or may not see anything. Okay, I don't even know what my window's set on at this stage. But right now it doesn't look like I'm seeing a whole lot. Okay. So I'm probably going to have to make an adjustment here. As I look at my function, definitely probably want to go to a y minimum of -30 because I had x squared minus 30. Definitely a maximum of at least 10 because I had a 10 in the linear part of the function. I'm just guessing here on what these could be. And I'll just do -10 to 10 for right now on these. Let's just see if that gives us anything. Okay, there's the quadratic. And there's the linear function. Okay, but that's not quite good enough because I need to be able to see a sectioned off region. And it looks like I need to let that linear function get a little bit higher on the left side. So let's let the y maximum here, let's let this be 30. Let's just try 30 and see if that catches it. Okay, so there's the first parabola. Well, I still didn't quite catch it, did I? Okay, so we'll try one more time here. Let's just let it be 50 and then I'll make sure I catch it. Okay, so I just play around with the window here. Try to find out, there we go. Okay, the region that we're interested in. Now we can clearly see the region we're trying to find is this region right here in the middle, the one that gets sectioned off. Okay, now if I want to set this up as a antiderivative problem, okay, well the first thing that I can look for is I can look for what will be the boundaries on this antiderivative. What's the lower boundary and what's the upper boundary? Okay. or the lower x-coordinate and the upper x-coordinate? Well, on the graph over here, the lower x-coordinate is going to be this x value right here, and the upper x will be this one right over here. We have to look where the two functions intersect. And we can do this one of two ways. We can set the quadratic equation equal to the linear and try to solve it by hand, or we can use sometimes calculators have shortcut functions on them that'll just find those numbers for you. Okay? This particular model, the 84, we have a second calculate feature here that will find intersections for us. Okay? The first curve is y1, so I push enter. The second curve is y2, so I push enter. And my guess on the first one, maybe -10 or something. Okay? Well, it's over around, it looks definitely at -8. Okay? So that's one way I can find these boundary points, is just use the calculator and let it find them. Or if you want to solve it by hand, you can also do that. Okay? Let me find the other one real quick. Second calculate intersect. And this one looks like it's over about 5. And it was right at 5. Okay? So that's how I decide what the boundaries are for my particular problem. I need to go from -8 to 5 because that's where the two functions intersect each other. Okay? All right, now, as I set up the antiderivative, I remember that there needed to be a subtraction in the middle. I just have to be a little careful on the order that I set these two functions up. I have to make sure that I do the upper function minus the lower function. Okay? And in this case, we can definitely tell the linear function between this intersection and this intersection, the linear function is higher the entire time. So I'm going to take, when I write this out, I'm going to write the linear function first because it's the upper function minus the quadratic function, which happens to be the lower function on my problem. Okay? And this is how we set up an area between curves type question. Okay? Now, from here, it's just like the problems that we did the last time. Okay, now we just need to take a whole bunch of antiderivatives. We need to sub in 5 and -8 and do all the calculation. I'm not as much worried about the actual computation today. I'm more worried about just getting the problem set up. Okay? So any questions with how I set this one up? I might recommend that if you get a problem like this, try to clean it up a little bit before you actually go through and take the antiderivative. And what I mean by cleaning it up, we've got a couple of numbers right here. And I don't mean that this is multiplication, okay? But I mean, let's just try to simplify this. You know, I've got a +10 here. This is a +30. I might as well join those together as a +40. Instead of doing 2 antiderivatives, now I only have to do 1. Okay? So if you do a little bit of algebra and just clean this up a little bit, rewrite it as 40 minus 3x minus x squared, it'll save you a little bit of time later on. Okay? But if you don't, you'll still get the right answer. It'll take you a little longer. Okay? All right, so there was one example. Let's look at another example here. First function is 2x cubed plus x squared plus x plus 5. And the second one is x cubed plus x squared plus 2x plus 5. Okay? So this time, 2 cubic functions. Okay? But again, I think the place to start, before we try to set this up, we need to graph both of these cubic functions and see where they intersect each other. We need to see what the region looks like that we're trying to find. So I type these in. 2x cubed plus x squared plus x plus 5. And the second one is x cubed plus x squared plus 2x, hit the wrong button there, plus 2x plus 5. And I'll graph it on the window that I have. I, again, may have to make some adjustment. Okay, there's the first cubic function. And, oh, wow, the second one is really close. Okay, so they're very close to each other, so I'm going to actually have to zoom in a little bit here so that I can see a better picture. I'll just try the automated zoom in feature on this calculator and see if I get a better look at it. Okay, there's the first one. And there's the second one. Okay, well, still not a very good look here. Okay. Let's try to zoom in one more time, but I'm going to move my cursor down a little bit so that I zoom in around the middle of the graph here. Okay, so here's the first curve, and here's the second curve. Okay. Now I might be in just a little bit too far. I mean, we're just going to have to keep trying to play around with this, and this is the disadvantage of using a calculator to try to find these things. Okay? Because we're just having to just manually guess and check, zooming in, zooming back out, and all those types of things. Okay? If we want to find all the intersections on this, we could just set this first equation equal to the second equation and solve for x algebraically, and then we wouldn't have to be doing so much of this guesswork here. Okay? So there's advantages and disadvantages to both here. I need to get this a little better here on the graph because I do need to point something out. Okay, this is going from negative here to here. So let's go from negative 2 to 2. And let's go up to about 9 on this. And let's just see what that looks like. Okay, we can kind of see this here. Now, the reason I want to bring this one up as this example, we can see that there is a sectioned off region right in here. Okay, and so this is one of the areas that we'll be trying to find is this region right in here. Okay, up here it kind of looks like these graphs cross again, and they do cross again. Okay, if I was able to get this to look a little nicer, this is also another region that we would be trying to find. Okay, now the major difference that I want to point out on this equation though is that when we try to set this up, well, let's go ahead and find all these intersection points first. Okay, let's find them all, and then it'll be easier for me to explain this idea here. Okay, so second calculate intersect. The first intersection is right at -1. Okay, so they cross at -1. The second one is at 0. I mean, it looks like it's 0 on the graph, but I know it's 0 because if I sub in 0 to both of these equations, I get 5 on both of them. So they do cross at 0. And then the third one, second calculate intersect, I'm going to guess it's at 1. Yeah, it is. Okay. All right, so my three intersection points are -1, 0, and 1. Now when I set up this function to do the antiderivative, I'm going to go from -1 to 0 first. I'm just going to go take this one region at a time here from -1 to 0. Now the question that comes up is, which is the upper function in that region? You know, which one is this upper one right here? Okay? And it's a little bit hard to tell, but if I do a trace, I can figure out which one it is. If I push trace here, okay, I need to start using my arrows to see where I'm at. Okay. Notice in the upper left-hand corner, I am on function y1, which is the 2x cubed function, and from -1 to 0 is at the upper function. And the answer is yes. Okay, so that's how you can use trace to tell you which one is the upper function. Okay, so from -1 to 0, I need to take the 2x cubed function minus the 1x cubed function. Whoops, I don't know if I wrote it. I don't know if I got it all copied down right. Okay, but I think you get the idea. Take the 2x cubed minus the 1x cubed function. Okay, and I would set that up, and if I did this calculation, I would find the area between -1 and 0. Now, why did I stop at 0? Why do I want to set up a separate one as I go from 0 to 1? Well, what happens if I just stay on y1 here? What happens once I get past 0? This 2x cubed function is now which function? It's the lower function. So when I calculate this area from 0 to 1, I need to switch my two functions around because this is now the upper function. So now it's going to be the x cubed function plus x squared plus 2x plus 5 minus the 2x cubed function. Okay? And so that's why we want to graph these initially so that we can tell what the regions look like. We can see, first of all, how many intersections there are. We had to find all three intersections. Okay? then I have to look at those intersections and I have to decide, is the upper function, is it always the upper function? Or if it is not, we need to do like I did here and split these regions apart and then add them together. Okay? Now again, my recommendation on this, make sure you clean this thing up before you actually go through and try to do an antiderivative. Okay? As I look at this here, 2x cubed minus x cubed, that's just 1x cubed. Notice some of the terms, like the x squareds, they cancel off. And if you don't cancel them off right away, you're going to be doing a lot of extra work that you don't really need to do because stuff's going to cancel out later anyway. Okay, so try to clean it up here. X minus 2x. This whole thing just drops all the way to x cubed minus x. And that's a much more manageable antiderivative than what we had up here at the very top to begin with. Okay, so just try to clean things up and it'll make your problems a little more manageable. Okay? All right, we'll see you next week.